Okay, problem 925 says an incandescent light bulb is an inexpensive but highly inefficient device that converts electrical energy into light. It converts about 5% of the electrical energy it consumes into light while converting the remaining 95% into heat. The glass bulb of the lamp heats up quickly as a result of absorbing all that heat and dissipating it to the surroundings by convection and radiation. Consider an 8 centimeter diameter, 60-watt light bulb in a room at 25 degrees C. The emissivity of the glass is 0.9. Assuming that 5% of the energy passes through the glass bulb as light with negligible absorption, and the rest of the energy is absorbed and dissipated by the bulb itself by natural convection and radiation, determine the equilibrium temperature of the glass bulb. Assume the interior surfaces of the room to be at room temperature. All right, so what we have here is, let's jot down some of our givens. Well, we have this light bulb, right? And this light bulb is going to be creating light, but at the same time, the resistance heating is generating a lot of heat that's being expelled out to the room. And I think we've all touched a light bulb that's been on for a while, and we know that it is very, very hot, right? So there's a lot of wasted energy in that creation of light. And what we're trying to find is, well, exactly how hot is that temperature of the surface, assuming that we're losing 95% of the, or we're turning 95% of a 60 watts of a light bulb into heat. So you see here at the bottom here it says, well, their light portion, or the amount of energy that goes into creating the light, is only 3 watts out of the 60. So the Q dot that actually turns into heat is the 0.95 times 60 watts of the light bulb, or 57 watts. Okay, so out of the 60-watt bulb, 3 watts become light, 57 watts become heat. So we have the heat transfer rate. We also know the diameter, so we're going to assume this light bulb is a sphere. So the diameter is 0.08 meters. We have the T infinity. The room is at 25 degrees C, and that's also equal to the temperature of the surroundings when you look at the radiation component. Okay, that's the temperature of the walls. We have the emissivity, 0.9, and that's about it. So what we're going to have to do is we're going to have to come up with the properties of air, and we always do that. This is a natural convection and radiation problem. We'll need to do that at the film temperature, and that is Ts plus T infinity over 2. Well, I don't know what Ts is, so to get the air properties, I'm going to have to guess. Okay, and intuitively, we've all probably touched a light bulb that's been on. We know it's very, very hot. So I'm going to take an initial stab at this and say, oh, it's roughly about 175 degrees. So I have 175 plus 25 divided by 2, and I've guessed a convenient surface temperature. So now that my film temperature is a nice round number, and it happens to be, that's 175 plus 25 is 200, divided by 2 is 100 degrees C. Okay, so that's my film temperature. I look up my properties of air. Well, beta, that's just equal to 1 over the film temperature in Kelvin, or 1 over 373. My kinematic viscosity nu is 2.306 times 10 to the minus 5 meters squared per second. My Prandtl number is equal to 0.7111, and my thermal conductivity K, 0.03095 watts per meter Kelvin. All right, so that's all my givens. And so I should mention one more thing. The heat transfer rate Q dot, this is the total amount of heat that's being generated. So that is going to equal the q dot due to natural convection plus q dot due to radiation. All right, so we'll have to keep that in mind. Well, this problem, so we have natural convection and radiation, so q dot total is equal to that q dot convection plus q dot radiation. Those equations look like, well, q dot convection is Newton's law of cooling, h times the surface area times Ts minus T infinity, and radiation is the emissivity times Stefan-Boltzmann constant times the surface area times Ts to the 4 minus T, well, minus T of the surroundings, but in this case we're told that surroundings are also equal to T infinity, okay? That raised to the 4. Now, this equation, these temperatures in the radiation have to be in Kelvin. Okay, so I'm going to rewrite this and write plus emissivity times sigma times the surface area times Ts plus 273 to the 4 plus T infinity plus 273 raised to the 4. Okay, so all I did there was convert my temperatures into Kelvin. All right, so we have the radiation part. We know what T infinity is. So we know T infinity. We don't know. We're looking to find what the surface temperature is. And the same thing's going to go for radiation. We're still trying to find that surface temperature. And we have everything, but in radiation, we don't know what the heat transfer coefficient is, H. But we know that anytime we're getting one of these heat transfer coefficients, we have to rely on experimental data. And when we're looking at natural convection, so now just talking about the natural convection component only, we have to calculate the Rayleigh number, okay? And the Rayleigh number, let's go to handy dandy table 9-1. We're doing flow over a sphere. That's what the light bulb is being modeled as. Characteristic length scale is the diameter, and we have this equation for the Nusselt number, all right, which is my non-dimensional heat transfer coefficient. So I can come back up here and calculate my Rayleigh number. My Rayleigh number, that happens to be G times beta times Ts minus T infinity times the diameter cubed divided by nu squared times Prandtl number times, equals G is 9.81, beta 1 over 373, Ts minus T infinity is Ts we're trying to find, T infinity is 25 degrees C, okay, times the diameter, 0.08 cubed, divided by nu 2.306 times 10 to the minus 5 squared times the Prandtl number, 0.7111. Okay. And I can punch that into my calculator and get 1.8 times 10 to the 4 times Ts minus 25. Okay, so this is what my Rayleigh number is equal to. Now, I can look at the equation for the Nusselt number. Okay, so from table 9.1 again, that was 2 plus 0.589 times the Rayleigh number to the 1/4 divided by 1 plus 0.469 over the Prandtl number raised to the 9/16, and the whole denominator raised to the 4/9. Okay. Well, punch stuff in, 2 plus 0.589, the Rayleigh number, based on the diameter to the 1/4, divided by 1 plus 0.469 over the Prandtl number, 0.7111, to the 9/16, to the 4/9. And the Nusselt number then, that is going to equal 2 plus 0.4546 times the Rayleigh number to the 1/4. Okay?